Alright, let's talk about buffers. As soon as I get my pen action up here. There we go. Okay, I'm going to write in red. So, buffers, they're solutions that have the ability to resist changes in their pH when a strong acid or a base is added to them. They're important in a lot of chemical processes where pH we need it to be constant. There's many industrial applications where we want our products to be made under conditions where the pH is very constant, and so you'd want to ensure that happens. You'd want to have a buffer system in place. An example near and dear to us is the pH of our blood. It's about 7.35. If it drops below 7, the results are fatal. Not immediately. A day of this would put you in the hospital. If it goes above 7.7, the same thing is probably going to happen. Within a day, you'll end up in the hospital. And our blood has a buffering system. So, for example, hyperventilating. What's the big deal? So somebody's breathing fast. Who really cares? Well, physiologically, what happens is you start to breathe faster. You start to breathe out more CO2 than normal. With CO2, when it's dissolved in your blood, forms carbonic acid. Yes. So if the carbonic acid amount will start to go down, the pH starts to go up, and our body does not like this. There is a buffering system in place, but eventually it can be overcome. So our body's reaction to this is to constrict blood flow to your brain so you pass out and your breathing returns to normal. If we are conscious and somebody is around to help us, they'll often have you breathe into a paper bag, and that is so that you would hopefully be breathing more CO2 back into you to try to undo what the hyperventilating is doing. But more often than not, you pass out, and then everything returns to normal. Most buffers are made up of a weak acid and a sodium salt. And sodium is because if you remember grade 11 chemistry, sodium compounds are very soluble. So a sodium salt would completely break apart into its two ions. Now in labs, a common buffer is a sodium salt, sodium acetate, and acetic acid. So here's the two reactions that are taking place in the container. So I drop in my sodium acetate. It completely breaks apart. So I got lots. Yes, I got lots of this stuff, and this is the one that I'm interested in. And it also is acetic acid is put into the water, and I've got acetic acid, and it is a weak acid, and I have therefore lots of this. Not much of this is going to break apart to form this and this. And on top of that, I got a ton of this sitting around, which makes this want to dissolve even less. Common ion effect, KSP. So let's talk about what happens to this scenario, when I add in an acid. So I just want those two reactions there. Perfect. So I add in an acid. In reaction to what's going to change, this is going to go up. If I add in an acid, this goes up. And what happens to this equilibrium? It's Le Chatelier's principle. If the concentration of this goes up, it's going to shift left to undo that change. Now, in order to be able to go left, I have to have this and this. And luckily, while I just added this concentration is going up. And do I have CH3COO minus in my container? Yes, look. Yes, yes, I've got lots. So this reaction goes this way. I add in a bit more, boom, it goes this way, uses it up. I add in a bit more, boom, it goes this way, uses it up. And this thing will resist change in pH. The concentration of H3O plus ions will not go up immediately, even though I'm adding in H3O+. Now I'm going to go down to another set of these same reactions, so I knew I was going to be writing on them. What happens if I add in a base? If I add in a base, well, there's no OH minus here. But if I add in a base, what will happen to this guy? If I add in OH minus, and there is some H3O plus around, those two things are going to join together to give me 2 waters. So if I add in OH minus, this thing will go down. And in response, according to Le Chatelier's principle, what's going to happen? This reaction will shift right to make some more. It can only go right if I got this stuff. Do I have water? Oh, it's an aqueous solution. I got lots of this. Do I have this? Yeah, I got lots of this because it's a weak acid. So I got lots and lots. So OH minus goes in. This gets smaller. Boom, it goes right to make more. More OH minus. This gets even smaller. Boom, it shifts right to make even more. Eventually, though, I'm going to run out of this, and it's going to stop. Now, there is a limit to how much H plus or H3O plus that I can add. A buffer can absorb without undergoing significant changes in pH. So if I made a little graph, and this is pH, as I add in add more H3O plus, the pH would stay relatively constant, and then at a certain point this reaction, this system is unable to hold back a change in pH, and it goes and it takes off. There are calculations along with this idea of a buffer system, but I don't talk about them in grade 12. You can deal with the math when you're in grade or in university next year. There is a few examples in our textbook of the math, but again, I'm not interested in it. But I'm interested in you understanding the concepts of what a buffer is.